Okay, we want to continue our discussion about electric fields. And what I want to do is do a calculation for the electric field of a continuous charge distribution. This is prototype 5 calculation. And what I show is a charge distribution along the y-axis of length L. And our point of interest is along the x-axis at P in distance h. So the rod shown along the vertical axis has a uniform charge density, or uniform charge Q. It has length L, so the question is, what is the linear charge density? As within all these videos, your best results will come about if you pause the video when a question or a problem statement is asked. Try it yourself and then look to see what I've done. Okay, as we see, the charge density is given by the total charge divided by length, and that's going to give you charge per unit length. So if I want the total charge, I would want, again, just simply multiply by the length, and I have total charge. Now we're interested in calculating the electric field E at point P. And for a point charge, what is the electric field given by? If in fact all I had was a point charge, let's say it's located at distance L or whatever, but what's the general relation for finding the electric field at a point charge? Pause the video. And of course, for a simple point charge, E is given by K sub E Q over R squared times R hat. Now choose a piece, a small element of the rod to represent an infinitesimal contribution to the electric field at P. That's going to be essentially a point charge. We're going to treat it as a point charge. So take a moment and choose your element. As you can see, I've chosen my element and I've decided to put it up here in blue, and I'm going to label it DQ. And that is an infinitesimal piece of the rod that we can treat for the time being just as a point charge. Now, what is the contribution to the electric field from the infinitesimal piece, that little bit of charge? What is the electric field due to that piece at point P? Once again, pause the video and try to work it out. Well, that little contribution to the electric field we're going to call dE. And that's given by KE dQ over R squared R hat. And notice that it's very similar to what we did in 2, except that we're trying to notate that it is due to an infinitesimal piece, and it's only a infinitesimal contribution, an elemental contribution. Now, what is the variable denoting the distance of dQ from the origin? Once again, pause and think about it. Y. As you can see, I've drawn this distance y here from the origin to the infinitesimal element. Now, we can think of this in terms of what would we need to sum to add each little contribution up to make up the total electric field at P. And of course, as we sum up, we move along the y direction. So we can immediately begin to assume that we're going to be integrating along the y-axis. Now, what is the vector from dQ to P. Go ahead and draw it on your paper what the vector is from DQ to P. And of course, I show the vector here in green where R is equal to X I hat, because there's my component along the x-axis making up that vector, minus Y hat, Y along the J hat direction. And Y is the Y component along the y-axis that make up this total vector R. And if I wanted to get the unit vector, remember that all I have to do is multiply or divide by the length R. So the unit vector is equal to x over r I hat minus y over r j hat. Now you should be able to figure out what R is in terms of x and y. And that matter of fact, that was my next question. So go ahead and determine what R is in terms of x and y. And that's given by the square root of x squared plus y squared. Now, what is the contribution to the electric field from dq in terms of x and y? Well, that's given by dE equal to k dq over x squared plus y squared, there's your r squared term, times the unit vector representing r hat. Now what is dq in terms of dy? How do I get the little charge there in terms of dy? Pause the video and try to work it out. And dq is given by lambda dy. Now you should understand why that is the case. Lambda dy is one of the fundamental charge distribution elements. Now, what is the contribution to the electric field in terms of lambda dy? Go ahead and work the equation out. Pause the video. And of course, I show it here where the contribution to the electric field is given by Ke lambda dy over the distance squared times the unit vector from y, or from the charge element to the point P. At this point, you should be able to go ahead and integrate this and find the final value for E at point P. End of problem.